Hey guys, what's going on? Today we're going to be doing derivations for length contraction. This is a pretty unintuitive concept, so I'm going to show you a quick demonstration of what it is before we actually delve into the math around it. So for the scenario here, we have a person A that's at rest, staying on some hillside, lawn, whatever you want, he's going to be at rest. And then we have a train that has person B on it, and both the person and the train are both in velocity v. So as it moves across the screen, person B is going to record his velocity to be just v, because he's in the same frame as the train moving, and person A is going to record person B's velocity to be 2v, because you set the two vectors. But what about if the train isn't going v? What if instead it's going c, the speed of light? What happens then? Well, as it moves across, same exact scenario, person B would record his velocity be going v, because he's at the same reference frame as the train, so he's going the speed of light too, and on the speed of light train, he's moving v. But person A, you might say, he would view person B to go c plus v. But Einstein says that's not possible. He says that the speed of light is a maximum speed of the universe. You cannot exceed the speed of light. So what happens now? Well, Einstein also says that in this scenario, person B will be viewed by person A to be going the speed of light. Now, this can come off really confusingly. You might be saying, well, is the train not going to lose flight? Is person B not moving? Like, do you have to add the vectors? And Einstein says, usually yes. And it's still to a point correct. However, because the speed of light is the maximum speed of the universe, we must assume two things. First, that time is being stretched, which is simply time dilation, and distance is being contracted. That's length contraction. So we're really going to focus on the last part. Distance is being contracted. Now, hopefully you have a better grasp of what length contraction is. Now, let's show the math behind it, and that it really is a physical property. So here we have a very similar scenario to the first one, with the only addition being we now have a bar at the very end. So what we're going to do is we're going to have the train running to the bar, and then our entire goal is to record the length between the train and the bar from person B's reference frame and from person A's reference frame. So to do this, we're going to set two variables, length of A and length B. Simply the length that person A records, length that person B records. So here we're going to have the train go across, smack into the bar. And they're going to record the time it takes for that to happen. So we're going to set three variables right off the bat. The velocity of person A is 0, obviously he's at rest. The velocity of person B is v, he's moving at velocity v, and the velocity of the train is c, which is speed of light. Now, for the time, we can set this relationship, that time of A is equal to gamma, which is the Lorentz factor, times time B, the time that person B records. Now, we can use this to find the distance, as distance is simply velocity times time. Now, for finding length A, we can say the distance is just length A, the velocity is speed of light, and the time is the time that person A records. So, to put that into an equation, we have length A equals c times time A. There we have it, the length that person A records between the train and the bar before the train smacks into the bar. Now let's move on to length B. So length B would be the same as length A. It would be the speed of light times time B. However, we can rearrange the equation time A equals gamma times B to be times B equals time A over gamma. So we're just going to switch out time B with time A over gamma. So now we have length B equals c, speed of light, times time A over gamma, the Lorentz factor. Now, we also know that c times time A is equal to length A. So, switch out the variables once again, and now we have length B equals length A over gamma. Now we know gamma, which in this case is just the Lorentz factor, but gamma has to be over 1 unless both objects are at rest. Now we know clearly right here that the train's moving, the person's moving, therefore gamma has to be greater than 1. Because of this, we can tell definitively, without a doubt, that as long as both objects are not at rest, length b is shorter than length a. And that right there is length contraction. That the length that person B records is shorter than the length person A records. And you can think, okay, it's just like an illusion, because obviously there's only a distance that's pretty set, but Einstein says no. Einstein says it is the physical property of the object. That person B is not just viewing length B to be shorter. Length B actually is shorter. And similarly, person A isn't deciding that length A is shorter or longer than length B. It actually is longer. So that right there is length contraction. I hope this makes a little more sense. Like and subscribe. Have a great day.